Hi everyone, I'm Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today, I'm going to cover BJT configurations. So let us see overview of the today's session. So start with introduction, and we are introduce CBCECC configurations. So CB means common base configuration, common emitter configuration, and common collector configuration. And then followed by analysis of common base configuration. Then we'll talk about early effect or base width modulation, and then transistor parameters, then conclude with summary. So let us start. So we know what is transistor. Transfer resistance. Transistor means transfer resistance, as the signals are transferred from low resistance region to high resistance region. And BJT is a 3-terminal device, so whose terminals are emitter, base and collector, and it has a 2 p-n junction device, emitter base and collector base junctions. The BJT can be recognized by its operation. Operation depends on both majority and minority charge carriers, and based on that, so we have two types of BJT: bipolar junction transistor, NPN and PNP transistors. So you can view the block diagrams of these NPN and PNP transistor. This is NPN transistor, base terminal, emitter terminal, collector terminal. Here PNP transistor, base, emitter, collector. And symbolic representation of NPN and BJT. So this is your NPN transistor. How we can represent or how we can recognize a transistor is in NPN or PNP. So depending upon this arrow, so this arrow indicates the emitter current flowing out of the transistor, IE. So then it can be recognized as NPN transistor, and here the arrow into the transistor, that means the emitter current flowing into the transistor, hence it can be recognized as PNP. This is NPN and this is PNP transistor. So let us see what are the BJT configurations. Because transistor BJT is a 3-terminal device, so we can have 3 different configurations. It can be operated in 3 different configurations: common base configuration, common emitter configuration, common collector configuration. So these are the block diagrams or circuit diagrams for different configurations. First one is common emitter configuration. Here, see what is common emitter configuration. Emitter is grounded, or you can say emitter is common to both input port and output port. Then we can say it is common emitter configuration. In other words, we can also say this is a grounded emitter configuration. Similarly, second one, if you see this, if you observe here, this is your common base configuration, because base terminal is grounded here, or base terminal is common terminal to the input port and this is the output port. And similarly, we can also call this common base configuration as base grounded configuration. And common collector configuration, so here collector is common to both input port and output port. In other words, the common collector terminal is grounded here. Okay, so in this today's session, we are mainly focused on common base configuration. So due to time factor, so later sessions we will discuss common emitter and common collector. First, we mainly concentrate on common base configuration. So let us see the description of common base configuration. The base terminal is connected to the ground, and the input is applied between emitter base junction and output is taken between collector base junction. So this is base terminal and this is emitter terminal and this is collector terminal. Okay, and arrow is flowing, the emitter current flowing out of the transistor. The arrow indicates this is a NPN transistor. Okay, so here emitter base junction, input junction means emitter base junction. So we are giving input applied between emitter and base junction. So here we are giving input. Here across collector base junction, so this is emitter base junction and this is collector base junction, right? So across collector base junction we will take the output. So here, in order to use your transistor for amplification purpose, so we need to follow this rule. Emitter base junction is forward bias and collector base junction is reverse bias. So if the input section is forward bias and output section is reverse bias, then your transistor can be utilized for amplification purpose. Whereas if the input section is forward bias and output section is also forward bias, then we can say the transistor can be used for on switch. Similarly, if both are reverse bias, then we can say your transistor act as an off switch. So these are the few things we have to remember. So key features of common base configuration. So what are the key features? So its voltage gain is very high. Voltage gain means output voltage and by input voltage. So output voltage V0 by Vi, input voltage. So this is the general case of gain, voltage gain, right? So whereas here in common base configuration, what will be the output voltage? Output voltage is between collector and base, that is VCB. VCB is the output voltage, and what will be the input voltage? Vi will be the VEB, that is the voltage across emitter and base. VEB is the input voltage. So therefore we can write this as VEB by VCB by VEB for fixed values of output voltage. So here gain is very high in common base configuration and current gain. So whereas current gain means output voltage by input voltage. What is the output voltage here? Collector side. So that is IC. IC is the output current and IE is the input current. So therefore, what is current gain here? This is IC by IE. IC by IE is the current gain. So in case of common base configuration, it is represented with alpha. So alpha always less than 1. So current gain is less in case of common base configuration. Whereas power gain, moderate. Power gain is moderate and hence and also phase shift. So there is no phase shift between input and output. Applications. So these kind of common base configurations can be utilized in high frequency applications like RF amplifiers. So this is the overview of common base configuration. Let us see the analysis of common base configuration. So let us see. So to analyze the common base configuration, we have two conditions. So input characteristics and output characteristics. So first let us see the circuit diagram and its input characteristics. See here, the collector base voltage, that is VCB, is kept constant at 0 volt and the emitter current IE is increased from 0 in shootable equal steps by increasing VEB. So VEB is what here? Input voltage. And VCB is what here? Output voltage. And what about IE? IE is input current. So that means what is input characteristics of a common base configuration means it is the graph drawn between input parameters. What are the input parameters here? VEB and IE. Okay. So it is a graph drawn between input parameters VEB on x-axis and IE on y-axis for fixed values of output voltage, that is VCB. Right. So for different values of VCB, we have to increase VEB and we have to measure corresponding change in the input current, that is emitter current IE. So here if you see this circuit diagram, so this is a circuit to determine CB static characteristics, that is input and output characteristics. So here this is your common base configuration. Emitter is connected to the input across. This is biasing voltage VEE. In output side we are giving VCC. So these are the DC biasing voltages, and this is your VEB is the input voltage, that is voltage across, voltage between emitter and base. So this is the voltage between VEB. VEB. Why VEB? Why not VBE? So because here emitter terminal is on the top polarity, so we have to use VEB, right? So here in this case ammeter is used in order to measure the IE input current, and VEB voltmeter is used here, and this is to measure the VEB. Similarly in the output side, so output side is collector, IC is the output current. To measure this IC output current, ammeter, on ammeter we have to use, and voltmeter we have to use to measure the VCB, and this is the IB current. So however IB is equals to 0 almost, so because it is grounded, common base configuration. So if you see the characteristics of inputs, characteristics of common base configuration, first what we have to do, so the emitter is heavily doped, this we know. So the base is lightly doped and the collector is moderately doped. This is the basic structure of common base NPN transistor. Okay, and then what happened, this is repeated for, so first we need to VCB kept constant. So first I have to kept constant VCB at 0 degrees. So in such case, whenever VCB is, the output section is constant, means 0 volts. 0 volts means there is no current flow in the output section. So that means our BJT, the common base configuration, your transistor acts like a normal PN junction diode. So not 3 terminals. So this is your NPN transistor, right? So now output section I kept VCB is equals to 0 volts, means there is no current flow. So it just like acts like a normal PN junction diode. So we know the characteristics of normal PN junction diode. So until you reach the cut-in voltage, there is no current flow through the PN diode. So similarly here also there is no current flow until you reach the cut-in voltage. So 0.6 is for cut-in voltage is equal to 0.6 for silicon. So that means your transistor is manufactured with silicon. So therefore from this cut-in voltage the current rises abruptly. For this VCB is equals to 0 volts, right? So whereas second case I have increased the VCB greater than 1 volt. So what happens now? So that means we are increasing further VCB greater than voltage, greater than 1 volt means, so we are increasing the reverse bias voltage on the right side. So what happened? So there is a chance of decreasing the depletion region. So when depletion region decreases means there is a chance of emitter current, that is input current IE will flow through the output section. So that constitutes some current. So that doesn't require any input voltage VEB. So therefore this characteristic will shift towards the left side. See here. So this doesn't require any VEB and current flows through the diode, the emitter current. So this is the characteristics of your common base configuration. Now let us see what are the output characteristics of the common base configuration. So for a constant value of IE, IC independent of collector base voltage VCB. IC flows even for 0 VCB. This is the output characteristics. See here. So here what happened, output characteristics means it is the graph drawn between output parameters, particularly output voltage and output current. So what is the output voltage? VCB is the output voltage. This is VCB is the output voltage and output current is IC. So on y axis we take IC, on x axis we take VCB. So it is the graph drawn between VCB and IC for fixed values of input current. Input current is what? IE. So here this is the fixed. So for different values of IE, we need to increase the VCB. But here what happens when you apply, for example, IE is equal to some 0 volts, we kept IE at 0 millivolts, milliamperes. We kept IE at 0 milliamperes. In such case, what will be the output current? IC, right? So when we fix IE at 0 milliamperes, so from 0 volts, so we require some voltage, because already this is the output section is reverse bias. The output section already reverse bias, so it doesn't require any input voltage, but so there is a constant current flowing through the output side. So there is a constant current IC, because we are giving IE. So due to IE, there is a current flow, even though it is reverse bias. So, and similarly, if you further increase the IE value, so IE is now increased to 2 milliamperes. So this IE, because base is lightly doped, so this IE current will cross this junction and enter into the collector region. The IE current will cross the base junction and enter into the collector region, because base is lightly doped and very thin. So therefore, here this IE current, when IE increases, your current, collector current, output current increases. So for different values of IE, so only when current is given, emitter current, that current will flow through the collector. Corresponding collector current also changes, but it is constant. Even you increase this VCB, output voltage, there is no increase in the current, as in the case of previous input characteristics. So these are the output characteristics. Okay. So because output section is almost reverse bias and 0. So only if you apply this emitter current, then only there is a constant collector current. Right. So this is about output characteristics. One more important point, majority charge carriers enter into the base. The emitter current IE flows to the collector region as the base is lightly doped, and that constitute the collector current IC. So this is the main view of this output characteristics. Now, very important concept of early effect or base width modulation. See, early effect or base width modulation means the dependency of base width on the collector to emitter voltage VEB. So what are the consequences? What is base width modulation here? So base width modulation means, so this is your NPN transistor. NPN transistor, here this is base and this is emitter and this is collector, right? So when you apply reverse bias voltage, when you increase VCB, this voltage, what happens here? The reverse, because it is reverse bias, so we are increasing the reverse bias voltage. So when you increase the reverse bias voltage, what happens? The base width, or you can say the depletion width, actually this is the base width of total NPN transistor in case of common base configuration. Okay, so this is the total base width, right? So now, because it is very thin, here so there is a depletion region between this PN type, this is, let us say, this is PN diode. So this is the total base width, and due to increase in the reverse bias voltage, there is an increase in the depletion region between these PN diode. So what happens now? So the depletion region between these two PN diode is increases. Increases means what? Your total base width increases, effective base width increases. So therefore, the emitter current will enter into the collector region, and that constitute the collector current IC, right? So this is called base width modulation. So base will change, base width changes due to increase in the VCB. So this is about base width. Here the dependency of base width on collector to emitter voltage is nothing but base width modulation. It is also called as early effect. And what are the consequences of this early effect? There is a less chance for recombination in the base region, hence alpha increases. What is alpha? Alpha is IC by IE, which is less than 1. So 0.9852 to 0.99, something like this. It is less than 1. Just now we have discussed. Alpha increases as VCB increases, right? And where alpha is large signal gain or current amplification factor. Okay, so there is a less chance for recombination in the base region, means because base region is very less and it is very lightly doped, so charge carriers are very less and hence recombination takes place. Also the chances for recombination also very less. And one more important consequence is the charge gradient increases within the base, means minority carriers increases. Here in the base region, the charge carriers, so minority charge carriers, that very few minority charge carriers are there, but those minority charge carrier concentration also increases. And next one is, for extremely large voltages, the effective base width may be reduced to 0. So if you increase further, there is a chance of decrease in the base width, total base width. So sometimes it may be reduced to 0, and which causes breakdown in the transistor. And this phenomena is called punch through. See, this is another important concept, punch through. So if you further increase this voltage, then reverse bias voltage, there is a chance of effective base width may be reduced to 0. So which causes voltage breakdown in the transistor, and this phenomenon is called punch through. And alpha ranges from 0.98 to 985, approximately 99. So this is about early effect or base width modulation. Now let us see the transistor parameters, which gives because different dimensions, the parameters have different dimensions, hence it is called hybrid parameters. So parameters have different dimensions, hence those are called hybrid parameters or H parameters. This is also called H parameters of the transistor. So what is that? First one, input impedance. Input impedance or HIB. So we know that impedance. So as per Ohm's law, V is equal to IR. So from this we can recognize this as V by R is equal to V by I. So from that we can say that HIB impedance, input impedance means HIB equals to change in VEB. Change in VEB by change in IE. That means what? And that means this is regarding VEB, IE means what? These are the input parameters. So if you recollect the characteristics of input characteristics of common base configuration, VEB and IE are the input parameters. Okay, and this is when VCB is at some constant voltage. Next, output admittance, HOB. So it is the slope of the output characteristics. So whereas HIB is slope of the input characteristics and output admittance is slope of the output characteristics, its value ranges from 0.1 to 10 micromhos. So replica of the ohms, that is resistance opposite. So admittance HOB is given by delta IC by delta VCB. So IC and VCB, what? So these are the output parameters. So if you recollect the output characteristics of common base configuration, IC is the output collector current is the output current and VCB is the output voltage. So change in output current by change in output voltage when IE is equals to constant, that is IE means input current. So this is the output admittance. So next one, forward current gain, HFB. What is HFB? Slope of IC versus IE. Forward current gain. So as I already told, what is current gain? In common base configuration, alpha is equals to IC by IE, right? So here also HFB. HFB means change in output current IC by change in input current IE for fixed values of output voltage VCB. Similarly, and its value ranges from 0.9 to 1. So as we have already seen, the range from the alpha current amplification factor is 0.9 to 1. Similarly, reverse voltage gain HRB. So it is the slope of VEB versus VCB. So its value ranges from 10 power minus 5 to 10 power minus 4, and its expression is HRB is equals to delta VEB by delta VCB. Means what? Here reverse voltage gain. So actually voltage gain means what? What is the expression for voltage gain? Output voltage by input voltage. So what is the output voltage here? In case of common base, VCB is the output voltage. What is the input voltage? VEB is the input voltage. Correct. So here this is voltage gain. So reverse voltage gain means what? It is reverse. That is VEB by VCB. That means change in reverse gain indicates HRB. So change in output voltage by change in input voltage for fixed values of IE. So when IE is constant, then this is the expression for reverse voltage gain. So these are the different transistor parameters, hybrid parameters or H parameters, very important parameters. So this represents, these parameters represent the performance of the transistor. So let us conclude for today's session. So we have started with BJT configurations, and then we have introduced the what is common base configuration, common emitter configuration, and common collector configuration, and we have explained this with that those circuit diagrams also we have seen, and analysis of common base configuration. We have focused mainly on analysis of common base configuration, and we have seen the input and output characteristics of common base configuration. Then we have seen what is early effect or base width modulation, and we have seen transistor parameters and H parameters. These are the performance parameters of transistor. And then next we will discuss the analysis of CC and CE. Thank you.